Okay, let's dive right in. We're going to pull back the curtain on the math that our entire digital world is built on. We're talking about the hidden architecture of computation, and more importantly, what happens when the numbers don't quite add up the way you think they should. So let me start by asking you a really simple question. You've known this since, what, middle school? You take the square root of 3, and then you square it. The answer has to be 3. I mean, what else could it possibly be? Seems totally obvious, right? Well, here's the twist. On the very device you're watching this on, the answer might actually be 2.9999 something, or maybe 3.0000, something with a 1 at the end. It's super close, but it's not exactly 3. And that tiny, tiny difference, well, it turns out it's everything.
Now, hold on, this isn't some bug or a glitch in your computer. It's actually a fundamental feature of how computers have to deal with the messy, infinite world of real numbers. It all comes down to a problem of precision.
The core idea here is something called finite digit arithmetic. You know, think about a number like pi, or the square root of 3. The digits after the decimal just go on and on forever and ever. They never repeat. But your computer's memory? That's not infinite. It doesn't have endless shelf space to store an endless string of digits, so it has to make a compromise. And this slide right here shows that compromise perfectly. On the left, you've got the ideal perfect value of 5 divided by 7. But on the right, you see what a computer using something called 5-digit chopping would store. It basically calculates up to the 5th digit and then just chops off the rest. And poof, a tiny bit of information is lost. A tiny and what seems like a totally harmless error gets introduced right at the start.
So, one tiny little error. What's the big deal, right? Well, what happens when an algorithm has to do millions or even billions of these calculations, one after the other? What happens when these tiny errors don't just sit there, but they start to add up, and even worse, multiply?
To see what I mean, let's take a quick trip back to high school algebra. We're just going to solve this standard quadratic equation, but we're going to do it using a hypothetical computer that can only perform 4-digit arithmetic. That means it can only keep track of 4 significant digits for any number it works with. So how does our simple little computer do? Well, this is where it gets really interesting. For one of the two answers, it's actually pretty accurate. But for the other one, the one you see here, it's not even close. The real exact answer is negative 0.01611. Our 4-digit computer, though, it spits out negative 0.02000. That's a huge miss. How huge are we talking? Well, the relative error is a whopping 24%. And this all happened because the standard formula we all learned in school forced the computer to subtract 2 numbers that were incredibly close to each other. And that specific operation is famous for taking any tiny pre-existing errors and just blowing them up. A small precision problem cascaded into a really big mistake. And this gets us to the absolute heart of the matter. It's not just that small errors exist. The real question is whether the method you're using, the algorithm itself, causes those errors to shrink away into nothing or to grow and completely explode. And that, my friends, is the crucial difference between stable and unstable algorithms. I love this analogy because it illustrates the idea perfectly. A stable algorithm is like giving a little nudge to a giant boulder. That initial tiny error doesn't really change the final outcome in any meaningful way. But an unstable algorithm, that's like starting a tiny snowball rolling at the top of a huge, snowy mountain. That initial error gets amplified at every single step until it triggers a full-blown avalanche of nonsense. So to see this avalanche in action, let's look at a real example from the source material we used. We're going to solve what's called a system of differential equations. Now, don't worry about the name. These are basically the mathematical workhorses that physicists and engineers use to model how things change over time. We're going to use the exact same algorithm to solve this problem twice. The only thing we are going to change is one single tiny input, called the step size. You can just think of it as how big of a jump the algorithm takes as it calculates its way to the solution. Okay, first let's run it with a step size, or each, of 0.05. And would you look at that? The numbers in the approximation column are basically hugging the numbers in the actual value column. They're almost perfect. The tiny errors are being kept in check. This is a stable, reliable calculation. The boulder hasn't moved. Now hold on to your hats. All we're going to do is double that step size to 0.1. We change nothing else. And what we get is an absolute catastrophe. Just look at that approximation column now. The numbers don't just drift away from the real answer, they explode. They grow exponentially into complete and utter gibberish. This is the avalanche. The source material, which is a classic textbook on this stuff, they don't mince words. They literally call this outcome disastrous results. That's not me being dramatic. That's the textbook telling us the same method with one tiny change just completely failed. So why does any of this matter to you if you're not a numerical analyst? Because every single one of us is living in a world that is built, managed, and simulated by this exact kind of math. The accuracy of the weather forecast you checked this morning, the structural integrity of a bridge or skyscraper, the design of an airplane wing, the complex financial models on Wall Street, all of it depends on solving incredibly complex equations on computers, and their reliability, their trustworthiness depends entirely on using numerically stable algorithms that stop these error avalanches before they ever start. It really makes you stop and think, doesn't it? Our modern world doesn't just run on code, it runs on the very specific, very careful choices made by the people who write that code, choices about which algorithms to trust with our safety and our future. And that leaves us with a pretty big question. What other invisible algorithms are quietly shaping our reality, for better or for worse?